So, the last lecture we looked at the approximate liquid phase analysis except in a heuristic way, because you see the complications about these kind of problems are that you can never do the full math, okay, because the full math itself are basically research problems. Okay. So, we are just giving you ideas that how these problems are actually approached, okay, and that is how we are actually solving them. Okay. So, here we are going to put forward a comprehensive droplet vaporization model, and that will make things a lot clearer. Okay, a comprehensive droplet vaporization model. Now, what happens in the comprehensive droplet vaporization model is that we are going to look at all the phases now and we try to connect them actually together. Okay, so, that will give you the clear cut idea. So, here what happens is that you are assuming a scenario in which a droplet is injected into a gas field, gas phase flow field, right. Okay. That is where the droplet is actually injected. Okay. So, there are several assumptions that goes with it, that the gas flow is one dimensional. So, that means we are not really concerned so much about the gas flow. The initial droplet velocity is parallel to the gas flow, direction. Got it? So, it is like a droplet that is injected into a gas phase flow field, the droplet is velocity is parallel to the gas flow. So, we are going to analyze all the things that we have learned so far and put them in under one umbrella, so that you can understand them, right, that you can actually solve them also like that. So, the droplet motion, let us take the droplet motion first. This is the bulk motion of the droplet, dx by dt is equal to u, du by dt is equal to 3 CD by 2 Rs rho infinity by rho L. This you already know, I am just writing it so that you get the complete picture, right. If you recall, this is what we did in the drag, right, that is the change of velocity is basically given by the drag force, right, whereas the change in position of the droplet is basically given by the velocity, right. That is very simple, and dRs by dt, that is the rate of change of droplet diameter, is basically the vaporization rate, like that, right. And what did we learn earlier? That CD, the drag coefficient, is basically a function of Reynolds number, right, the external Reynolds number, where that Reynolds number once again is given by u infinity minus u Rs by. Okay. Now, this is basically what? This is the free stream density, it is not the mixture density, right, this is the free stream density, whereas this guy over here, okay, is basically the mu g is basically the air vapor mixture, and it is the average viscosity in the boundary layer. So, this boundary layer is basically the gas phase boundary layer, right. So, it is the average viscosity in that boundary layer, got it, clear. Okay. So, it is the average density in that boundary layer. So, this is CD, this is that. Now, one thing that you can readily see over here, that this Reynolds number is supposed to come down, right, the gas phase Reynolds number. Why? Because this depends on the relative velocity of the droplet and the free stream flow, right. So, when a droplet is injected into a flow field, it is natural that the droplet's velocity will increase, okay, and ultimately at some point of time it will become very close to the gas phase velocity, right, that is what happens. So, when that happens, this Reynolds number value is supposed to die down very quickly, right. So, you can expect a profile in which this Reynolds number will go down, right, that is supposed to happen. So, that is what you get from this analysis. Okay. So, the care is taken that you are computing the viscosity in the boundary layer, whereas you are taking the density in the free stream. Okay. Now, this mu g, now you can ask that how is mu g then calculated in the boundary layer, right, that is the next question. So, here we are going to answer each and every question that you might have. So, this mu g is calculated. So, you need two things, you need the temperature, right, because you need the temperature, because viscosity is a function of temperature, and you also need the composition, because with using the composition and the temperature you are going to find out what is the mean or the average viscosity will be in the boundary layer. So, that is calculated as T bar. So, that is where it is calculated. This is the surface temperature to some factor, and this is T infinity minus Ts. So, the temperature that is normal, because external temperature is T infinity, surface temperature is Ts. So, the boundary layer temperature will be somewhere in between, right. So, that is what the assumption is. So, this A we will come a little later what that is. Similarly, the composition is YFS on the surface, it is AR YF infinity minus YFS, right. So, here also this A is basically some averaging parameter, okay. And usually the value is 1/3. This is in some literature it is called the 1/3 rule, okay. So, it is basically what it means is Ts plus 1/3 T infinity minus Ts. So, this is like a weighting, okay. So, it is not like just the mean of the two, it is not like Ts plus T infinity by 2, it is not like that, right, because the temperature is predominantly Ts and there is a little bit of a contribution coming from the difference, right. So, this is, and similar thing happens with composition, okay. It is not Ts plus T infinity by 2, that is wrong, okay. So, this has come through experiments and empirical correlations, that this is called the 1/3 rule. This is how this viscosity is actually calculated. So, you can see it is biased more towards Ts than towards T infinity, you can see that, right, because it is a 2/3 1/3 kind of a rule, right. So, it is a 1/3 rule, that is what actually we call it in the literature, right. Okay. So, that is how the mu is calculated, the mu g is calculated. The CD, looking at now the variation of CD, because CD we said is a function of Reynolds number. So, that is given by 24 by Re, okay, Re to the power of 2/3 by 6. This is however valid for low gas phase temperature, not for high temperature systems, like for example plasmas or flames, okay, where the droplet can be even in a flame, right, it can be in a very hot flow, okay. So, it depends on the Reynolds number in this particular way. Now, many of these things are empirical, many of them are devised through experimental studies, okay, and that is how these numbers have come into the picture. Also, you should note that this is valid only for a droplet. If we have a spray configuration, for example, right, in a spray what happens, that the droplets are very close to each other, correct. So, in that way CD, okay, will also be a function of this inter droplet spacing. Let us call that some d prime. So, this d prime. So, it will be dependent on that inter droplet spacing also, right, in some way, we do not know how. That is why it is very hard to measure the CD for a cluster of droplets, because you do not know how they are going to behave, right. So, this is a empirical formulation valid for a single droplet. This term also has to be incorporated into this somehow, okay, because of the shielding effect that the droplet actually creates, okay. So, the CD, how the CD will depend on that, that is also an open ended question, got it. So, this actually takes care of the droplet motion part, whatever we did, this is droplet motion. The key takeaway things are that there is something called CD, which is a function of the Reynolds number. Reynolds number itself, okay, is a function of rho infinity, the relative velocity, which is u infinity minus u, and the corresponding mu g bar. This mu g bar requires evaluation of the film temperature. Film temperature is the temperature of the gas phase boundary layer, and there we have used the 1/3 rule, right. Using the 1/3 rule we have found out what is the mu g going to be. Got it? Okay. So, all this comes under a unique umbrella now over here. Okay. Now, so let us look at now what we are going to do about the gas phase analysis. Now, the gas phase analysis, okay, you should consult the previous lectures that we did, okay. And if you have forgotten some part of it, let me just recollect that gas phase heat and mass transfer are quasi steady. We have already explained many times why it should be quasi steady. We will do that one more time. Okay. Pressure drop in gas is negligible. Drop in gas is negligible. Okay. And thermophysical properties are evaluated at some reference temperature and is considered constant. Thermophysical properties are evaluated at some reference temperature, reference temperature and assumed constant. So, if you have forgotten why it is quasi steady, let me say that relaxation time of the gas phase, right, scales as r square, this is the viscosity into the Reynolds number, whereas the evaporation time usually scaled as root over of Reynolds number, if you recall the two arguments. So, for high values of Reynolds number, what we had was the relaxation time was much shorter compared to the evaporation time, right. So, we could assume that the droplet evaporates much slowly. By droplet evaporating much slowly, we mean that the diameter regression is very slow, okay. The gas phase quickly relaxes, okay, before the droplet actually vaporizes. So, it is basically a quasi steady solution. This we considered much earlier, and we showed why that is the case. This is just to remind you that this is what actually happens. Now, we also said now the convective transport, this is important. Convective transport is basically caused by friction, or in other words the relative motion. Friction is due to relative motion, the relative motion between gas and droplet. Okay. So, what we do here in this particular case is employ the film theory. Okay. So, what is film theory means? Okay. As the name suggests, it is basically nothing but a thin boundary layer, let me put it that way. It is like nothing but a film of the vapor mixed with the gas that exists in the vicinity of the droplet, very close to the interface, right. So, this assumes that the resistance to heat and mass transfer between the surface and the gas may be modeled as gas films of constant thickness. So, this is basically what is it? This is basically a boundary layer concept, right. So, there what we mean is that there exists a thin gas film, right, of thickness dt and dm. One is the mass, one is for the temperature, one is the thermal, and one is the corresponding mass basis. Okay. Between a gas, this is there exists a thin film of thickness there between the surface, right, and the gas phase, that is the bulk gas phase. It is exactly the same as a boundary layer concept, okay, and this is what provides the resistance, okay, to the heat and mass transfer that happens between the gas phase and the liquid phase, right. So, this is what is actually provides the resistance. Okay. Okay. So, we are going to model this is the source of resistance basically. Got it? Okay. So, that part should be clear. So, now if you look at for a non-vaporizing sphere, for a non-vaporizing sphere, what happens is that delta T naught is given by 2 Rs divided by Nusselt number 0 minus 2, and we will come to that. The corresponding MO okay. You remember that Nusselt number is a function of Reynolds number and Prandtl number. This you know from your heat transfer. This is a function of Reynolds number and Schmidt number, right. So, for a non-vaporizing sphere that is the case. So, this essentially assumes that it is a conduction model, right. Non-vaporizing sphere is a conduction model. Okay. So, this assumes that there is conduction or diffusion through the film must be equal to the actual intensity of the convective transport, right. So, in other words, if we have to write it, this assumes diffusion or conduction transport through the film must be equal to the actual intensity of the convective transport between surface and flow. Got it? Okay. So, for evaporating droplet, same expressions are used basically. So, this is for non-evaporating, right. So, for evaporating droplet, so that was non-evaporating. So, you could get that very easily done. For non-evaporating we use the same thing. Now, we incorporate the effect of surface blowing. Okay. So, what happens in the evaporating droplet is that you vaporize the liquid, right. So, there is some kind of a surface blowing. So, this is almost equivalent to the problem that you have a flow over a flat plate, there is some kind of a surface blowing happening through the plate. What happens with that? The boundary layer gets actually extended, right. So, there is a thickening of the laminar boundary layer, so to say, right. So, imagine the same thing is like a droplet, there are vapors are being vented out, right, because of evaporation rate, right. So, if there is a boundary layer that existed on the liquid surface, right, on the liquid surface there is some kind of a boundary layer, right, that boundary layer usually is extended or it becomes thicker. Okay. So, this is called the surface blowing or Stefan's flow. So, it affects Stefan's flow basically affects delta T, delta M, etc. Okay. So, in other words, it thickens the boundary layer, right. It thickens the boundary layer, that is what it does, right. So, in other words, to take into account that thickening, we introduce correction factors. So, the correction factors are Ft is basically given by dt by dt 0, and so it is basically just but some ratio. So, this is m divided by dm 0, right. So, these were basically for the non-vaporizing cases, right. Now, if we assume that the distribution of temperature and fuel vapor are uniform across the droplet surface, okay, we can safely comment that Ft is basically a function of the Spalding heat transfer number, and Fm is basically a function of Bm, that is the mass transfer number. This happens because we have uniform temperature and concentration and fuel vapor concentration along the droplet surface. Got it? So, along the droplet surface we have this uniform vapor concentration, right. Okay. So, we can write it like that. Now, based on all these things, m dot, which is the vaporization rate of the liquid, can have actually two forms, okay, instantaneous vaporization rate. One is given by this rho g dg Rs, Sherwood number Bm. The other one equivalent kg, or it can be written as alpha g lambda g also, Cpf Rs Nu star ln 1 plus Bt, right. One comes from the heat transfer argument, one comes from the mass transfer argument. We already know this, right, because of these two evaporation rates. These are the two functions. Okay. Now, one might ask which one to use between the two. Now, that is a complicated question. What do you think, which one should be used normally? Because normally Bm is not the same as Bt, right. We just established that it is only equal to Bt when your Prandtl number and Schmidt numbers are the same, right, but it is normally not equal, correct. So, when can we actually use it? We can use it, which one to use it, okay, that depends on which one is a rate limiting step, right. So, actually the smaller of the two is basically what actually governs, okay. That means you can transfer a lot of heat, okay. So, if it is only heat basis, you can evaporate it probably at a faster rate, but it is the mass limitation. That means still this accumulated vapor around the droplet has to be transported out for the next level of evaporation to take place, right. So, it becomes that which one is a rate limiting step over here, and that is important, okay. So, it depends on which one is the rate limiting phenomena, heat or mass. So, the smaller of the two is basically what is called the rate limiting. So, Cpf bar that we have written over here, right. So, that requires this particular guy that you see over here is basically nothing but the average specific heat in the film. Film means that boundary layer, right. Whereas, this rho g bar d g bar ks bar or kg bar rather, kg bar is basically the average density binary diffusion coefficient, okay, and thermal conductivity of gas mixture in the film, okay, got it. So, that is how you evaluate it. The evaluation part is not that difficult, okay. So, we have also introduced two numbers like Sherwood number star, that is basically 2 plus the Sherwood number for the non-vaporizing case divided by this Fm that we just now said, okay. Similarly, there is a Nusselt number counterpart to it, that is nothing but 2 plus Nusselt number 0 minus 2 divided by Ft, okay. So, you can imagine that when there are no surface blowing effect, this becomes the same as the Nusselt number 0, right. This also becomes the same as this. So, when there is no evaporation means Fm is equal to 1, Ft also will become equal to 1. So, naturally what happens when this becomes 1, this 2 and that 2 gets cancelled, you are left with the Nusselt number 0, right. So, that means it is the same as a non-vaporizing sphere, which is quite obvious, right. Okay, when there is surface blowing, you have a different value of Sherwood number and Nusselt number because of that surface blowing effect, because of the thickening of the laminar boundary layer and things like that, right. Okay. It is also imperative to write once again to remind you guys that what is the Bm. So, Bm was Yfs minus Yf infinity minus Yfs, and the corresponding Bt was Cpf bar. This is once again I have written it as, we could have written it as Hs also, that was not a problem, and this is L effective, where L effective, if you recall, was the latent heat plus it can be any QL by m dot also. Remember, this QL was the amount of heat that was going inside the liquid phase, right. Okay. And L was basically the latent heat. If you recall your earlier classes, that is what we did in those classes as well. Got it? Okay. So, now that this stars are basically called the modified Nusselt numbers, right. Star, SH star are modified Nusselt numbers. Nusselt numbers. The actual Nusselt numbers are, these are modified, right. Actual Nusselt numbers are, actual Nu and SH are, this is given from the first definition, right. If you look at the definition of Nusselt number, this is what the definition is. At the surface, right, that is what Nusselt number is, right, and SH is given as 2 Rs divided by Yfs minus Y dyf by dr at S, right. Got it? These are the actual definitions of the Nusselt number that you can see over here. So, these Nusselt numbers, these are the two definitions of the Nusselt numbers that we have. This is the generic, right, the definitions. Okay. So, these two Nusselt numbers and Sherwood numbers are linked with each other, the modified and this Nusselt number is given as Nusselt number star ln 1 plus Bt divided by Bt. Okay. Okay. Right. So, these are the two definitions of a, if you include. So, this includes the heat and mass transfer numbers over here. Okay. So, in the next lecture we are going to go through now and look at the liquid phase, okay, as well as the gas phase once again, revisit it and try to cast everything actually together, right. So, this lecture ends here.